On November 11, 2025, astronomers at the Nordic Optical Telescope in the Canary Islands captured something remarkable. A comet from beyond our solar system, named 3I Atlas, was glowing in their images with a complex pattern of jets and tails stretching more than 1 million kilometers through space. This was no ordinary comet. This visitor had travelled through the darkness between the stars for billions of years before arriving at our cosmic doorstep. And right now, in these very days, it is racing away from us, speeding back into the depths of space where it will vanish forever. The window to study this ancient traveller is closing fast. What makes something from another star system so special? Why are scientists around the world pointing their most powerful telescopes at this icy wanderer? And what secrets might it carry about worlds we may never reach? Stay with me, and we will walk through one of the most exciting astronomical discoveries of our time. Let's start at the beginning, on a summer night in Chile. On July 1st, 2025, a robotic telescope called Atlas was scanning the southern skies, looking for asteroids that might someday pose a threat to Earth. Atlas stands for Asteroid Terrestrial Impact Last Alert System, and its job is to spot moving objects in space. That night, the telescope's camera captured a faint smudge of light, barely visible against the backdrop of stars. At first, astronomers were not sure what they were seeing. Was it an asteroid, a comet from our own solar system, or something else entirely? Within hours, other telescopes around the world swung into action. Astronomers in Arizona, Hawaii, France and Spain all pointed their instruments at this mysterious object. What they discovered was astonishing. The object was not circling the sun like the planets do. It was not even following the stretched-out oval path that most comets follow. Instead, it was moving on what scientists call a hyperbolic trajectory. Think of it like this. Imagine throwing a ball straight up in the air. It goes up, slows down, stops, and falls back down. That is like an orbit. But now imagine throwing that ball so hard that it never comes back. It just keeps going, faster and faster, never slowing down enough to turn around. That is what 3I Atlas is doing. It came into our solar system from somewhere else, and it is leaving, never to return. On July 2nd, 2025, the Minor Planet Center, which is like the official record keeper for objects in space, made an announcement. This was not just any comet. This was an interstellar comet, only the third one humans have ever seen. The letter I in its name stands for interstellar. The number 3 means it is the third such object we have discovered, and Atlas is the name of the telescope system that found it. So when you see 3I Atlas written down, you are reading a label that tells a story. The third visitor from another star system, spotted by the Atlas survey. But how do scientists really know it came from beyond our solar system? The answer is in the math and the speed. When astronomers measured how fast 3I Atlas was moving, they found something incredible. Relative to the Sun, this comet was travelling at 58 kilometers per second when it entered our solar system. That is more than 200,000 kilometers per hour. To put that in perspective, a jet airplane flies at about 900 kilometers per hour. This comet was moving more than 220 times faster than a jet. No object born in our solar system naturally moves that fast. Even our fastest spacecraft, like the Voyager probes that left Earth decades ago, do not move nearly as quickly. The only way for something to be moving that fast is if it came from somewhere else, accelerated by the gravity of a different star system billions of kilometers away. Scientists also traced 3I Atlas backward through space, like running a movie in reverse. When they did this, they found that the comet came from the direction of the constellation Sagittarius, near the center of our Milky Way galaxy. This is unusual. The previous 2 interstellar visitors came from other directions. This one arrived from the southern part of the sky, travelling on a path that brought it through the plane where most of the planets orbit. This alignment is rare, happening by chance only about 1 in 500 times. It is not impossible, just uncommon, and it made the discovery all the more interesting. Let's talk about what 3I Atlas actually is. Picture a dirty snowball the size of a small mountain tumbling through space. Scientists believe the solid nucleus, or core, of this comet is somewhere between 440 meters and 5.6 kilometers across. That is a big range because the comet is so far away and so faint that it is hard to measure exactly. To give you a sense of scale, 440 meters is about as long as 4 football fields placed end to end, and 5.6 kilometers is about the distance you might walk in an hour. So we are talking about something that could be as small as a large building, or as big as a small city. This nucleus is made mostly of ice, not just water ice, though there is plenty of that. This comet also contains frozen carbon dioxide, which is the same gas you breathe out and the same stuff that makes the bubbles in soda. It probably has frozen carbon monoxide too, and maybe even methane and ammonia. These ices formed billions of years ago in the cold outer reaches of another star system, far from any sun, where temperatures are so low that even gases freeze solid. The nucleus is also mixed with dust, tiny grains of rock and metal that were floating around when that other solar system was born. As 3I Atlas got closer to our sun, something beautiful happened. The sun's heat began to warm the surface of the comet. The ices on the surface started to sublimate. Sublimation is when a solid turns directly into a gas without melting first, like dry ice when you take it out of a freezer. The gas streaming off the comet carried dust particles with it, and this mixture formed a glowing cloud around the nucleus called a coma. The coma is what makes comets look fuzzy in telescopes. It can grow to be thousands of kilometers across, much larger than the solid nucleus itself. The coma of 3I Atlas was a few thousand kilometers wide, which means you could fit several Earths side by side inside it. The sun's light and the solar wind, which is a stream of charged particles flowing out from the sun, pushed the gas and dust away from the comet, forming a tail. Comet tails always point away from the sun no matter which direction the comet is moving. It is like the sun is a giant fan, blowing the tail backward. Some comets have two tails, a dust tail that looks yellowish and curves gently, and a gas tail that looks bluish and points straight away from the sun. Observers watching 3I Atlas reported seeing its tail grow longer and more complex as it approached the sun. By November, the tail stretched across a noticeable part of the sky, visible even through small telescopes if you knew where to look. Now, let's talk about the journey 3I Atlas took through our solar system. When it was first spotted on July 1st, 2025, it was already inside the orbit of Jupiter, about 670 million kilometers from the Sun. Jupiter orbits at about 780 million kilometers from the Sun, so 3I Atlas had already crossed into the inner part of our solar system by the time we noticed it. But here is the amazing part. Astronomers went back and looked at old images taken by other telescopes before the comet was discovered. These are called pre-discovery observations. By searching through archives, they found images of 3I Atlas going all the way back to May 21, 2025, more than a month before it was officially discovered. This helped scientists figure out the comet's path much more precisely. The comet continued its journey inward, speeding up as the sun's gravity pulled on it. On October 3, 2025, it passed close to Mars, only 28 million kilometers away. That might sound like a lot, but in space terms, it is pretty close. Spacecraft orbiting Mars had a chance to take pictures of the comet from a nearby vantage point. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express spacecraft both turned their cameras toward 3I Atlas. Even though their cameras were designed to photograph the surface of Mars, not distant comets, they managed to capture images showing the comet's fuzzy coma. These observations from Mars helped scientists figure out the comet's exact position and path 10 times more accurately than before. Then came the big moment. On October 30th, 2025, 3I Atlas reached perihelion, which is the point in its orbit closest to the Sun. At perihelion, the comet was about 202 million kilometers from the Sun, just inside the orbit of Mars. Mars orbits at about 228 million kilometers, so 3I Atlas came slightly closer than that. At this distance, the comet received intense sunlight. Each square meter of its surface was being hit with about 770 watts of energy, which is like having several bright light bulbs shining on every small patch of ice. This heat caused even more ice to sublimate, making the coma brighter and the tail longer. But here is the tricky part. For observers on Earth, perihelion was a problem. The comet passed behind the Sun from our point of view. Imagine you are trying to watch a bird fly past a bright streetlight at night. Right when the bird crosses in front of the light, you cannot see it because the light is too bright. That is what happened with 3I Atlas. From late October through early November, the comet was too close to the Sun in the sky for telescopes on Earth to observe it. The Sun's glare drowned out the faint light from the comet. So even though perihelion was when the comet was most active, Earth-based observers had to wait patiently for it to reappear on the other side of the Sun. Fortunately, some spacecraft were in better positions. Weather satellites and solar observatories, which are designed to look at the Sun, caught glimpses of 3I Atlas as it passed nearby. NASA's GOES-19 weather satellite spotted it. So did a spacecraft called the Solar and Heliospheric Observatory, which watches the Sun constantly. These observations helped fill in the gap, giving scientists valuable data even when Earth-based telescopes could not see the comet. By November, 3I Atlas had moved past the Sun and was visible again from Earth, this time in the early morning sky just before sunrise. Astronomers were excited to see how the comet had changed after its close encounter with the Sun, and what they saw was fascinating and in some ways surprising. The comet was brighter than before, about 5 times brighter in some measurements. It had developed long, complex jets of gas and dust stretching in multiple directions. Some of these jets pointed toward the Sun, which is unusual. Most comet tails point away from the Sun, but 3I Atlas seemed to have jets going both directions, creating what astronomers call an anti-tail. This is where things get really interesting, and where scientists start to scratch their heads a bit. A research team led by Professor Avi Loeb at Harvard University has been studying 3I Atlas closely, and they have noticed several features that make this comet different from typical comets in our solar system. One of these features is the anti-tail, a jet of material pointing toward the Sun. Anti-tails have been seen in a few other comets before, but they are rare and usually explained as an optical illusion caused by the angle we are viewing the comet from. However, Professor Loeb and his colleagues argue that the anti-tail of 3I Atlas is not an illusion. It is real material flowing sunward, pushed back by the force of the solar wind hitting it. The fact that this jet has persisted for months suggests that a lot of gas is flowing off the comet, enough to create a visible structure even against the pressure of the Sun. Another unusual feature is the comet's chemical composition. Telescopes like the James Webb Space Telescope and the Hubble Space Telescope have been observing 3I Atlas, analysing the light it gives off to figure out what it is made of. These observations revealed something unexpected. 3I Atlas has more carbon dioxide than typical comets from our solar system. It also showed higher amounts of nickel compared to iron. In most comets, nickel and iron appear together in roughly equal amounts because they are released from the same types of molecules. But in 3I Atlas there was a lot more nickel at first, and only later did iron start to show up as the comet got closer to the Sun. This changing ratio puzzled scientists. It might mean that the ices in 3I Atlas have a different chemical structure than the ices in our own comets, perhaps because they formed under different conditions around a different star billions of years ago. Then there is the mystery of the missing tail. After 3I Atlas passed perihelion, scientists expected to see a big, bright cometary tail pointing away from the Sun. This should have happened because so much material was being blown off the comet by the intense sunlight. But in some images taken in early November, the tail was surprisingly weak or even absent. The comet looked more like a fuzzy ball than a classic comet with a long, sweeping tail. This was strange because the comet was clearly active. It was releasing gas and dust. So where was the tail? Some scientists wonder if the material being released is different from what typical comets release, or if it is being pushed in unusual directions by magnetic fields or solar wind in ways we do not fully understand yet. Professor Loeb has raised the possibility that 3I Atlas might not be a natural comet at all. He and his team have written papers suggesting that some of its features could be explained if it were an artificial object, like a spacecraft or probe from another civilization. This idea is controversial, and most astronomers are skeptical. They think the features of 3I Atlas, while unusual, can probably be explained by natural processes we just do not fully understand yet. Comets are complicated and can behave in surprising ways, especially when they come from other star systems where conditions might have been different. But Professor Loeb argues that scientists should keep an open mind and consider all possibilities, even ones that sound like science fiction. He points out that the best way to settle the question is to gather more data and study the comet as closely as possible while we still can, and that is the challenge. 3I Atlas is moving fast. It is now heading back out of the solar system, and the window to observe it is closing. As of mid-November 2025, the comet is about 206 million kilometers from the Sun, roughly the same distance as Mars. From Earth, it is about 300 million kilometers away. That is twice the distance from Earth to the Sun. At this distance, the comet is faint, requiring a fairly large telescope to see it. It will continue to fade as it moves farther away, and the sun's heat no longer warms it enough to produce a bright coma. By December 2025, 3I Atlas will be even farther out, and by the spring of 2026, it will be passing near Jupiter, about 54 million kilometers away from that giant planet. After that, it will keep going, out past the orbits of Saturn, Uranus and Neptune, and eventually into the vast empty space between the stars. Once it leaves, it will never come back. The comet's hyperbolic orbit means it is not bound to our sun. It is just passing through, a visitor on a journey that will continue for millions of years as it drifts through the Milky Way galaxy. So why does this matter? Why should we care about a comet that is here today and gone tomorrow? The answer lies in what 3I Atlas represents. This comet is a messenger from another solar system, a piece of a world we will never visit. It carries with it clues about how planets and comets form around other stars. By studying its composition, scientists can compare the chemistry of our solar system with the chemistry of the system where 3I Atlas was born. These comparisons help us understand whether our solar system is typical or unusual, and whether the conditions that led to life on Earth might be common or rare in the galaxy. Interstellar objects like 3I Atlas also help scientists estimate how many such objects are drifting through space. Before 2017, we had never seen an interstellar visitor. Now, in less than a decade, we have spotted 3. The first was 1I Oumuamua, discovered in October 2017. The second was 2I Borisov, discovered in August 2019, and now we have 3I Atlas. Each of these visitors was different. Oumuamua was strange and mysterious, with an elongated shape and no visible coma or tail, leading to wild speculation about what it might be. Borisov looked like a normal comet, with a bright coma and a classic tail, reassuring scientists that interstellar comets might not be so different from our own. And Atlas is somewhere in between, clearly active like a comet, but with unusual features that challenge our expectations. Researchers have tried to trace back where these 3 visitors came from. A recent study by Chokros Kakarov and Professor Abraham Loeb used computer simulations to follow the paths of the 3 interstellar objects backward through the galaxy. They found that each one came from a different part of the Milky Way and has a different age. 3I Atlas is the oldest, with an estimated age of about 4.6 billion years, similar to the age of our own solar system. It likely originated from an older population of stars in the thick disk of the Milky Way, a region farther from the galactic plane where older stars tend to be found. Oumuamua, on the other hand, appears to be much younger, only about 1 billion years old, and came from the thin disk where new stars are still forming. Borisov is in the middle, about 1.7 billion years old. This diversity suggests that interstellar objects are being ejected from planetary systems throughout the galaxy's history, not just from young systems. How many interstellar objects might be passing through our solar system right now? Scientists estimate that at any given time there could be thousands or even tens of thousands of interstellar visitors within the orbit of Neptune. Most of them are far too small and faint for us to see. We only notice the rare ones that come close enough or are big enough to catch our attention. As our telescopes get better, we will start to find more of them. The Vera C. Rubin Observatory, which is expected to begin operations soon in Chile, will scan the sky so deeply and so frequently that it might detect 1 interstellar object per year. This will transform our understanding of these cosmic wanderers and help us build a catalogue, much like we have done with asteroids and comets from our own solar system. What is it like for a comet to travel between the stars? Imagine the loneliness of it. For millions or even billions of years, 3I Atlas drifted through the darkness of interstellar space. Out there, the stars are so far apart that the nearest one is just a point of light, no brighter than the stars you see in the night sky. There is no sun nearby to warm the comet. The temperature is only a few degrees above absolute zero, the coldest temperature possible. In that frigid emptiness, the comet is silent and unchanging, frozen solid, with no coma or tail, just a dark chunk of ice and rock tumbling slowly through the void. Then, after an unimaginable journey, the comet enters a new solar system. As it approaches the sun, things begin to change. The sun's gravity bends the comet's path, pulling it inward and speeding it up. The sun's light starts to warm the surface. For the first time in millions of years, the ice begins to sublimate. Gas streams off the surface, carrying dust with it. The coma forms. A tail grows. The comet comes alive. For a few brief months, it is a glowing visitor, visible to anyone with a telescope, and then, as quickly as it arrived, it leaves, heading back into the cold and the dark for another endless journey. This is the story of every interstellar comet. They are travellers on a scale that is hard to imagine, ambassadors from worlds we will never see. They remind us that our solar system is not isolated. We are part of a galaxy filled with billions of stars, most of which probably have planets, and many of which probably have comets. Some of those comets are thrown out of their home systems by the gravity of giant planets, or by close encounters with passing stars. Once freed, they drift through space, carried along by the rotation of the galaxy. Most of them will never encounter another star, but a lucky few, like 3I Atlas, stumble into a new solar system, giving the inhabitants, if there are any, a chance to see something from somewhere else. Scientists dream of doing more than just observing these visitors. They want to send spacecraft to study them up close. The European Space Agency is preparing a mission called Comet Interceptor, scheduled to launch in 2029. This mission will be unique. Unlike previous Comet missions, which were sent to visit specific comets already known, Comet Interceptor will be launched without a target. It will travel to a point in space called the Sun-Earth Lagrange Point 2, which is about 1.5 million kilometers from Earth in the direction away from the Sun. There, it will wait, drifting in space, ready to spring into action when a suitable comet is discovered. The spacecraft is designed to intercept a long-period comet, one that is visiting the inner solar system for the first time, or possibly even an interstellar object if one happens to come by at the right time. Comet Interceptor will consist of 3 spacecraft travelling together. When they reach the target, they will separate and fly past the comet from different angles, taking pictures and measurements from multiple viewpoints at the same time. This will give scientists a 3-dimensional understanding of the comet's structure and composition. The mission is being designed as a fast response system, ready to go at a moment's notice once a target is identified. If an interstellar object were discovered heading inward, and if its speed and trajectory were right, Comet Interceptor might be able to reach it. This would be humanity's first close-up look at a visitor from another star system. Imagine what we might learn from such a mission. By flying past an interstellar comet, we could measure its exact size and shape. We could analyze the gases streaming off its surface to determine the precise chemical composition. We could photograph the nucleus in detail, seeing the craters, cliffs, and jets on its surface. We could measure the dust particles in the coma, finding out what minerals they contain. All of this information would tell us about the conditions in the star system where the comet formed. It would be like receiving a letter from a faraway place, a message written in ice and dust, telling us what it is like out there in the broader galaxy. But even if Comet Interceptor does not get to visit an interstellar object, the data we have already collected from 3I Atlas is incredibly valuable. Scientists have used some of the most powerful telescopes ever built to study this comet. The Hubble Space Telescope, which orbits Earth, took sharp images of 3I Atlas on July 21, 2025, when the comet was still relatively far from the Sun. Those images showed a teardrop-shaped coma, with the comet's nucleus at one end and a faint glow extending in the other direction. The James Webb Space Telescope, which is even more powerful than Hubble, observed 3I Atlas on August 6, 2025, using its near-infrared spectrograph. This instrument breaks down the light from the comet into a rainbow of colours, revealing the chemical fingerprints of the molecules in the coma. Webb detected water vapour, carbon dioxide, and other compounds. Ground-based telescopes also played a crucial role. The Gemini North Telescope in Hawaii, the Lowell Discovery Telescope in Arizona, and many others around the world took turns observing 3I Atlas. Amateur astronomers joined in too, using their backyard telescopes to capture images of the comet and share them online. This collaboration between professional scientists and amateur enthusiasts is one of the beautiful aspects of astronomy. Everyone can contribute, and every observation adds to our understanding. One of the most innovative observations came from spacecraft orbiting Mars. As mentioned earlier, the European Space Agency's ExoMars Trace Gas Orbiter and Mars Express both observed 3I Atlas in early October 2025. These spacecraft were designed to study Mars, not comets, but their cameras were able to photograph 3I Atlas as it passed relatively nearby. The observations from Mars provided a different angle, allowing scientists to triangulate the comet's position much more accurately. This was a valuable exercise not just for studying the comet, but also for practicing planetary defense techniques. If a dangerous asteroid or comet were ever on a collision course with Earth, Being able to track its position precisely from multiple locations would be crucial for figuring out how to deflect it or prepare for its arrival. Now let's take a moment to think about the broader picture. Why are interstellar objects important for understanding the galaxy? The answer has to do with planet formation. When a star like our Sun is born, it forms from a giant cloud of gas and dust in space. As the cloud collapses under its own gravity, it starts to spin faster, forming a disk around the newborn star. In this disk, tiny grains of dust stick together, gradually building up into larger and larger objects. Eventually, these objects become planets, moons, asteroids, and comets. But not everything stays in the system. Sometimes, a comet gets too close to a giant planet like Jupiter and is flung outward by the planet's gravity. If the comet is moving fast enough, it escapes the star's gravity and becomes an interstellar object, drifting through the galaxy forever. This process happens in every planetary system, which means the galaxy is filled with debris from countless star systems, all mixed together in the space between the stars. Interstellar objects are like samples from this vast cosmic collection. By studying them, we can learn about the diversity of planetary systems in the galaxy. Do all systems produce similar comets? Or are there big differences depending on the type of star, the distance from the galactic centre, or the age of the system? These are questions we are just beginning to explore. 3I Atlas gives us a clue. Its high carbon dioxide content and unusual metal ratio suggest that the chemistry in its home system might have been different from the chemistry in our own solar system when it formed. Maybe the molecular cloud that gave birth to 3I Atlas's star had more carbon dioxide and less water than the cloud that formed our Sun. Or maybe the comet formed farther from its star, in a colder region where carbon dioxide ice was more common. These differences help scientists test their models of how planetary systems form and evolve. Each interstellar visitor is a data point, a puzzle piece in the big picture of galactic diversity. There is also a philosophical side to all this. Finding interstellar objects reminds us that we are not alone in the galaxy. I do not mean that in the sense of finding alien civilizations, although that is a possibility some scientists consider. I mean it in the sense that our solar system is one of billions, and the processes that formed Earth and the other planets are happening all over the galaxy, all the time. Somewhere out there, around another star, planets are forming right now. Comets are being flung into interstellar space. And maybe, just maybe, a comet from our solar system is passing through someone else's neighbourhood, giving them a glimpse of where we came from. This brings us to an important concept, the age of 3I Atlas. Scientists estimate that this comet is about 4.6 billion years old, which is roughly the same age as our own solar system. This means 3I Atlas formed at around the same time Earth was forming. While Earth was growing from a collection of smaller rocks and ice, and while the Sun was settling into its steady glow, 3I Atlas was doing the same thing in another star system far away. And yet, here it is now, crossing paths with us. It is a time traveller in a sense, carrying with it the frozen memory of an ancient past. The universe is full of these connections. The atoms in your body were made in stars that exploded billions of years ago, scattering their material into space. That material eventually became part of the cloud that formed the Sun and Earth. In a similar way, the ice and dust in 3I Atlas came from a different cloud, around a different star, but the elements themselves, the carbon and oxygen and nitrogen, all came from earlier generations of stars. We are all made of stardust, as the astronomer Carl Sagan famously said, and so are the comets. Let's shift gears and talk about the human side of discovering and studying 3I Atlas. Imagine being one of the astronomers who first noticed this faint dot of light in the telescope images. At first, you might not realize what you're looking at. It could be an asteroid, or a comet from our solar system, or maybe even a glitch in the camera. But as you measure its motion and calculate its orbit, you start to see something unusual. The orbit does not close, it is not bound to the Sun. And then the realization hits you. This is from outside our solar system. This is only the third time in human history that we have seen such a thing. Your heart starts to race. You call your colleagues, you double-check the calculations, and then, once you are sure, you make the announcement. The discovery becomes public, and telescopes all over the world start pointing at this tiny visitor, trying to learn everything they can before it disappears forever. This is exactly what happened in July 2025. The Atlas team in Chile made the initial detection, and within hours, observatories everywhere were mobilizing. The discovery was confirmed and announced on July 2, 2025. By that time, scientists had already gone back through old data and found earlier images of the comet, extending the observational record back to May. Every new image and measurement helped refine the orbit and build a picture of what this object is and where it came from. For the scientists involved, this is the kind of opportunity that comes along maybe once in a career. Interstellar objects are rare. We may only see a few in our lifetimes. Every observation counts, every data point is precious, and there is a sense of urgency because the comet will not stay around. It is already on its way out, and once it is gone for good. This urgency drives astronomers to work long hours, to share their data quickly, and to collaborate across borders and disciplines. The study of 3I Atlas has brought together experts in cometary science, planetary defense, spectroscopy, orbital dynamics, and more. It is a global effort, a testament to what humans can achieve when we work together toward a common goal. Now let's talk about some of the tools and techniques that made this discovery possible. The Atlas survey, which found 3I Atlas, is not a single telescope but a network of 4 robotic telescopes located in Hawaii, Chile, and South Africa. These telescopes scan the GAN sky every night, taking wide-field images to detect anything that moves or changes. The system was originally designed to find near-Earth asteroids that could potentially impact our planet, but it is also excellent at finding comets and other transient objects. Each night, the telescopes generate millions of data points, and powerful computers process these data to identify objects of interest. When something unusual is found, the system automatically alerts astronomers, who can then follow up with more detailed observations. Once 3I Atlas was detected, other telescopes joined the effort. Some of these are large research telescopes like the Gemini North and South telescopes, which have mirrors 8 meters across, making them among the largest optical telescopes in the world. These big telescopes can collect a lot of light, allowing them to see faint objects and take detailed spectra. Spectra are like chemical fingerprints. When you pass the light from a comet through a device called a spectrograph, it splits the light into its component colors, revealing dark or bright lines at specific wavelengths. Each element and molecule produces a unique pattern of lines, so by analyzing the spectrum, scientists can figure out what the comet is made of. Space telescopes also played a critical role. The Hubble Space Telescope, orbiting about 550 kilometers above Earth, has been taking pictures of objects in space since 1990. Its position above the atmosphere gives it a crystal-clear view, free from the blurring and distortion caused by air. Hubble's images of 3I Atlas showed incredible detail, revealing the structure of the coma and helping to estimate the size of the nucleus. The James Webb Space Telescope, which launched in 2021 and is stationed about 1.5 million kilometers from Earth, is even more powerful. Webb observes in infrared light, which is invisible to our eyes but very useful for studying comets, because many molecules emit infrared light as they are heated by the sun. Webb's observations of 3I Atlas provided some of the most detailed chemical information we have about this comet. All of this technology, from ground-based surveys to space telescopes, represents decades of investment and innovation. It is the result of thousands of engineers, scientists, and technicians working together to build the tools we need to explore the universe. And every time we discover something like 3I Atlas, it validates that effort and inspires the next generation to keep pushing the boundaries of what we know. Let's pause for a moment and recap what we have learned so far. 3I Atlas is a comet from outside our solar system, discovered in July 2025 by the Atlas survey in Chile. It is travelling on a hyperbolic orbit, meaning it will pass through our solar system once and then leave, never to return. The comet is a few kilometers across, made of ice and dust, and it comes from an older population of stars in the thick disk of the Milky Way galaxy. As it approached, the Sun, the comet, became active, forming a coma and tail. It reached its closest point to the Sun on October 30th, 2025, and is now heading back out into interstellar space. Scientists have observed it with telescopes on Earth and in space, as well as with spacecraft orbiting Mars. These observations have revealed unusual features, including high carbon dioxide content, an anti-tail pointing toward the Sun, and changing metal ratios, all of which make this comet a fascinating subject of study. Now, let's look ahead. What happens next? As of mid-November 2025, 3I Atlas is still visible in the morning sky before dawn, though it is getting fainter. By December, it will be even more difficult to see, requiring large professional telescopes to detect. Through the winter and spring of 2026, the comet will continue its journey outward, passing near Jupiter in March. After that, it will gradually fade from view as it moves beyond the reach of even our most powerful telescopes. By the end of 2026, 3I Atlas will be just another silent traveller in the darkness between stars, invisible and unknowable, carrying its secrets back into the cosmic ocean. But the story does not end when the comet disappears. The data collected during these few months will keep scientists busy for years. They will analyse the spectra, refine the orbital calculations, compare 3I Atlas to other comets, and build computer models to understand its unusual features. Every detail matters. The exact shape of the coma, the timing of the jets, the ratios of different chemicals, the brightness variations over time, all of these clues help paint a picture of what this comet is and where it came from. And most importantly, the lessons learned from 3I Atlas will help us prepare for the next interstellar visitor. Because there will be a next one. The discovery of 3 interstellar objects in less than a decade suggests that these visitors are more common than we once thought. Before Oumuamua in 2017, many astronomers assumed that interstellar objects were so rare that we might never see one. Now we know that they pass through the inner solar system regularly, perhaps a few times per decade or even more often. We're simply getting better at spotting them. As our survey telescopes improve and our detection algorithms get smarter, we will find more and more of these cosmic messengers. Each one will be unique, with its own story to tell. What makes each interstellar object different? The answer lies in their origin. Every planetary system is unique. Some stars are larger and hotter than our Sun, while others are smaller and cooler. Some systems have giant planets like Jupiter close to their star, while others have their giants far away. The location of giant planets matters because they are the ones that fling comets into interstellar space. If a system has a Jupiter-like planet close to its star, it will eject comets early in its history, and those comets might be rich in certain chemicals. If the giant planet is far from the star, the comets it ejects might have a different composition. The distance from the galactic centre also matters, because stars in different parts of the galaxy formed from gas clouds with different chemical makeups. 3I Atlas, being about 4.6 billion years old, formed at a time when the Milky Way galaxy looked different than it does today. Stars were being born at a higher rate back then, and the mix of elements in the interstellar gas was different. The star that 3I Atlas came from was probably similar to our Sun, but it might have formed in a region of the galaxy where the balance of carbon, oxygen, nitrogen, and other elements was slightly different. Over billions of years, that star has moved through the galaxy, orbiting the galactic centre multiple times. The comet, meanwhile, was ejected from that system early on and has been wandering ever since, a relic of an ancient time and place. There is something deeply poetic about this. 3I Atlas has been travelling for so long that the star it came from might not even exist anymore. Stars like the Sun last for about 10 billion years, so if the parent star was similar to the Sun, it is probably still shining somewhere out there. But we have no way of knowing where. We cannot trace the comet's path back accurately enough to pinpoint which star it came from. The motion of stars around the galaxy is too chaotic, and small uncertainties in the comet's trajectory multiply over millions of years, making it impossible to know for sure. It is like trying to figure out where a single leaf came from after it has been blown around by the wind for hours. You know it came from a tree, but which tree? The information is lost in the chaos. This uncertainty is both frustrating and beautiful. It means that 3I Atlas is truly a mystery, a visitor whose origins are forever unknown. And yet we can still learn from it. We can study its chemistry, compare it to our own comets, and use it to test our theories about how planetary systems form and evolve. We can measure its size, track its motion, and watch how it responds to the sun's heat. All of this is valuable, even if we never know exactly where it came from. Let's talk about what might happen if we could send a spacecraft to 3I Atlas. This is not something we can do right now because the comet is already on its way out and moving too fast for any spacecraft we have to catch up. But imagine if we had the technology. What would we want to do? First, we would want to take close-up pictures of the nucleus. This would tell us about the surface features. Are there craters from impacts with other objects? Are there smooth areas covered in fresh ice? or rough areas covered in dust? Are there active regions where jets of gas are shooting out, and if so, what do those regions look like? Second, we would want to collect samples of the gas and dust streaming off the comet. This could be done with instruments that fly through the coma, scooping up particles and analysing them on the spot, or even capturing some to bring back to Earth. Analysing these samples would give us a direct look at the material that makes up an interstellar comet, something we have never done before. We could compare the isotopes, which are different forms of the same element, and see if they match the isotopes in our solar system or if they are different. Isotope ratios are like fingerprints. They tell you about the conditions under which something formed. Third, we would want to measure the comet's magnetic field, if it has one, and the way it interacts with the solar wind. This would tell us about the internal structure of the comet and how it formed. And fourth, we would want to study the orbit in exquisite detail, measuring the tiny forces that act on the comet, like the pressure of sunlight pushing on the dust particles and the rocket effect caused by gas streaming off one side more than the other. These small forces can change the comet's trajectory, and understanding them helps us predict where interstellar objects will go in the future. All of this is wishful thinking for 3I Atlas, but it is not wishful thinking for future interstellar visitors. Missions like Comet Interceptor are being designed with exactly these goals in mind, and if we are very lucky, one of those missions might intercept an interstellar object within the next decade or two. When that happens, it will be a milestone in human exploration, the first time we have touched something from another star system. Now let's broaden our view and think about the other two interstellar objects we've seen, Oumuamua and Borisov. Comparing these three visitors helps us understand the diversity of interstellar objects and gives us clues about what might be out there waiting to be discovered. Oumuamua was the first. It was discovered on October 19, 2017 by the Pan-STARRS telescope in Hawaii. The name Oumuamua is a Hawaiian word meaning scout, or messenger from afar arriving first. It was a fitting name. Oumuamua was unlike anything we had seen before. It was elongated, shaped something like a cigar or a pancake, with a length about 10 times its width. It did not have a visible coma or tail, even though it passed close enough to the sun that any ice on its surface should have started to sublimate. This lack of cometary activity made some scientists wonder if it was more like an asteroid than a comet. But then something strange happened. As Oumuamua was leaving the solar system, astronomers noticed that it was accelerating slightly, moving faster than it should have based on gravity alone. This extra acceleration was small, only a few centimeters per second, but it was measurable and real. The most likely explanation is that Oumuamua was outgassing, releasing a small amount of gas that acted like a tiny rocket, pushing the object forward. But if that was the case, where was the coma? Why couldn't we see the gas? Some scientists suggested that Oumuamua might have been covered in a layer of organic material that formed a crust, trapping the gas underneath and releasing it in invisible jets. Others proposed more exotic explanations, including the possibility that it was a piece of alien technology, like a solar sail. Most scientists think the natural explanations are more likely, but the mystery of Oumuamua remains unsolved. Then came Borisov, discovered on August 30, 2019, by amateur astronomer Gennady Borisov, using a telescope he built himself in Crimea. Borisov was different from Oumuamua. It looked like a normal comet, with a bright coma and a long tail. It was easy to see that this was a chunk of ice and rock, not some strange, inactive object. Scientists were thrilled because it gave them a chance to study an interstellar comet that behaved the way they expected comets to behave. Observations of Borisov revealed that it had a lot of carbon monoxide, more than most comets in our solar system. This suggested that Borisov came from a very cold part of its home system, far from its star, where carbon monoxide could freeze into ice. The comet also had a different dust-to-gas ratio than typical solar system comets, and its nucleus appeared to be quite small, probably less than a kilometre across. Borisov passed through our solar system without any major surprises. It reached perihelion in December 2019, putting on a nice show for astronomers, and then continued on its way, leaving the solar system in early 2020. It was a textbook interstellar comet, and the data collected from it has been incredibly useful for understanding what interstellar objects are like. Now we have 3I Atlas, which is different from both of its predecessors. It is more active than Oumuamua, with a visible coma and tail, but it has unusual features that make it more mysterious than Borisov. The anti-tail, the high carbon dioxide, the changing metal ratios, and the sometimes missing tail all make 3I Atlas a puzzle. It is as if nature is showing us that interstellar objects come in many varieties, and we should not assume that any two will be alike. What can we learn from comparing these three visitors? First, we learn that interstellar objects are diverse. They can be active or inactive, large or small, carbon-rich or carbon-poor. This diversity probably reflects the diversity of planetary systems in the galaxy. Second, we learn that interstellar objects can be ejected from their home systems at different stages of those systems' evolution. Oumuamua, being relatively young, was probably ejected recently from a system that is still forming planets. Borisov, being middle-aged, came from a system that is more mature, and 3I Atlas, being as old as our solar system, was ejected long ago, perhaps during the chaotic early days when planets were still migrating and giant impacts were common. Third, we learn that detecting and studying interstellar objects is hard but possible. Each discovery has pushed the limits of our technology and required rapid coordination between observatories around the world. The fact that we have now found 3 interstellar objects in less than a decade is a testament to how much our capabilities have improved, and as we continue to improve, we will find more, building up a database of interstellar visitors that will help us understand the galaxy in new ways. Let's imagine what the future might hold. Suppose that by the 2030s, we are finding several interstellar objects every year. With enough of them, we could start to do statistics. We could ask questions like, what fraction of interstellar objects are active comets versus inactive asteroids? What is the typical size? What is the typical composition? Do objects from the inner galaxy have different chemistry than objects from the outer galaxy? Are there any objects that seem truly anomalous, objects that cannot be explained by natural processes? Each new discovery would add to our understanding, filling in the blanks and helping us see the big picture. We might also start to classify interstellar objects into different categories, the way we classify asteroids and comets in our own solar system. We have carbonaceous asteroids, which are rich in carbon and water, and we have rocky asteroids, which are mostly made of silicate minerals and metals. We have short-period comets, which orbit the Sun every few years, and long-period comets, which take centuries or millennia to complete one orbit. In the same way, we might develop a classification scheme for interstellar objects, based on their composition, size, activity level, and other properties. This would make it easier to talk about them and to compare new discoveries to previous ones. There is also the exciting possibility that we might someday detect an interstellar object before it enters the solar system. Right now, we only find these objects after they have already passed close to the Sun and are on their way out. But imagine if we could spot one while it was still far away, out past the orbit of Neptune, heading inward. That would give us months or even years to prepare. We could plan observations in advance, choosing the best times and the best telescopes to study the object. We could even plan a spacecraft mission, launching a probe to intercept the object and study it up close. This might sound like science fiction, but it is technically possible with the next generation of telescopes and spacecraft. One concept that has been proposed is a fleet of small, lightweight spacecraft that could be launched quickly and cheaply, ready to intercept any interstellar object that comes along. These spacecraft would not carry much in the way of instruments, but even a simple camera and a basic spectrometer would be enough to provide valuable data. The key advantage of having many small spacecraft is redundancy. If one mission fails, there are others to back it up. And because the spacecraft are small and cheap, it is easier to justify the risk. Another idea is to use powerful ground-based lasers to push a lightweight spacecraft to extremely high speeds. This concept, sometimes called a laser sail, would involve a spacecraft with a large, thin sail made of reflective material. A laser on Earth would shine on the sail, and the pressure of the light would accelerate the spacecraft to a significant fraction of the speed of light. At those speeds, a spacecraft could potentially catch up to an interstellar object, even one that is already leaving the solar system. This technology is still in the experimental stage, but it is being actively researched, and it might become a reality within the next few decades. All of these ideas are speculative, but they are grounded in real science and engineering. They represent the kinds of missions that could be possible if we are willing to invest in the technology and take on the challenge. And the payoff would be enormous. The chance to study material from another star system up close, to answer questions that we can only guess at from a distance, and to take the first steps toward exploring the galaxy beyond our own solar system. Now let's talk about the role of citizen scientists in discovering and studying interstellar objects. Astronomy is one of the few sciences where amateurs can make real contributions. The discovery of Borisov by Gennady Borisov is a perfect example. He was not a professional astronomer with access to a giant telescope. He was an amateur who built his own instrument and spent his nights scanning the sky, looking for anything unusual. And he found something incredible, something that has been studied by the most powerful telescopes in the world. His discovery shows that you do not need a doctorate or $1 million grant to contribute to science. You just need curiosity, dedication, and the willingness to look. Today, there are thousands of amateur astronomers around the world who contribute to the search for comets, asteroids, and other objects. Many of them share their observations online, posting images and data that can be used by professional scientists. There are also citizen science projects where volunteers help analyze telescope data, looking for objects that automated algorithms might have missed. These projects are fun and educational, and they genuinely help advance science. If you're interested in astronomy, there are many ways to get involved, from joining a local astronomy club to participating in online projects. The discovery of 3i Atlas, while made by a professional survey, has benefited from the contributions of amateur astronomers as well. In the weeks after the discovery was announced, amateur astronomers around the world took pictures of the comet, helping to track its brightness and activity. Some of these observations were made with telescopes that cost less than a good camera, proving that you do not need expensive equipment to do meaningful work, and the data collected by these amateurs has been shared with professional scientists, adding to the overall understanding of the comet. This collaboration between professionals and amateurs is one of the things that makes astronomy special. It is a science where everyone can participate, regardless of their background or resources, and it is a science that inspires people, young and old, to look up at the night sky and wonder about our place in the universe. Every time an interstellar object is discovered, it reminds us that the universe is vast, mysterious, and full of surprises. It reminds us that there is always more to learn, always another discovery waiting just beyond the edge of our current knowledge. Let's take a step back and think about the philosophical implications of interstellar objects. What does it mean that we are now finding visitors from other star systems? For most of human history, we did not even know that other stars had planets. The first confirmed exoplanet orbiting a Sun-like star was not discovered until 1995, less than 30 years ago. Now we know that planets are common, and that most stars probably have them. We have found thousands of exoplanets, ranging from giant gas balls bigger than Jupiter to small rocky worlds like Earth. Some of these planets are in the habitable zone, the region around a star where temperatures are just right for liquid water to exist. And where there is water, there might be life. Interstellar objects are a piece of this puzzle. They are the debris of planetary systems, the leftovers that did not get incorporated into planets. By studying them, we learn about the building blocks of planets and the processes that shape planetary systems. We also get a sense of how common certain conditions are. If every interstellar comet we find has lots of carbon dioxide, that might tell us that carbon dioxide is common in the universe, which has implications for the kinds of planets that form and the kinds of atmospheres they might have. If we find that interstellar comets are chemically diverse, that tells us that planetary systems are diverse too, which means there are probably many different kinds of planets out there, some similar to Earth and some very different. There is also the tantalizing question of whether interstellar objects could carry life. This idea is called panspermia, and it has been around for a long time. The basic concept is that life might spread from one star system to another, hitching a ride on comets or asteroids. If a comet from a system with life were to crash into a planet in another system, it might seed that planet with the building blocks of life, or even with living microbes. This sounds far-fetched, but it is not impossible. We know that some microbes can survive in the harsh conditions of space, at least for short periods, and we know that rocks can be blasted off the surface of one planet and land on another. Meteorites from Mars have been found on Earth, proving that material can travel between planets within our own solar system. Could material travel between star systems? The distances are much greater, but the timescales are also much longer. A comet travelling through interstellar space for millions of years might eventually encounter another star system. If that comet carried frozen microbes, and if those microbes somehow survived the journey, they might be able to colonize a new world. Most scientists are skeptical of panspermia, at least as a major mechanism for spreading life, because the conditions required are so extreme, but it is an intriguing idea, and one that is worth considering. If we ever do send a spacecraft to intercept an interstellar object, one of the things we would want to check is whether it carries any organic molecules, the building blocks of life. Finding complex organic molecules on an interstellar comet would not prove that life exists elsewhere, but it would suggest that the ingredients for life are common in the universe, which would be an important discovery. Let's talk about the concept of time and distance in the context of interstellar objects. When we look at 3I Atlas, we are looking at something that has been travelling for an incredibly long time. If the comet was ejected from its home system 4.6 billion years ago, it has been wandering through the galaxy ever since. The Milky Way galaxy is about 100,000 light-years across, and it takes our Sun about 230 million years to complete one orbit around the galactic centre. In the time that 3I Atlas has been travelling, our Sun has completed about 20 orbits around the galaxy. The comet, meanwhile, has been on a different path, drifting through the space between stars, occasionally passing near other stars but mostly travelling through the emptiness. To put this in perspective, think about the age of the Earth. Our planet is about 4.5 billion years old. Life appeared on Earth at least 3.5 billion years ago, maybe earlier. The first complex life, animals and plants, appeared about 600 million years ago. Dinosaurs roamed the Earth from about 230 million to 65 million years ago. Modern humans appeared only about 300,000 years ago, and recorded human history goes back only about 5,000 years. 3I Atlas has been travelling for longer than all of that. It predates not just human history, but the entire existence of complex life on Earth. It is older than the dinosaurs, older than the first fish, older than the first cells. It is a relic of the very dawn of the solar system. And yet, here it is, passing through our neighbourhood right now, at this moment in time. Out of all the billions of years it has been travelling, it happens to be here during the tiny sliver of time when humans exist and have the technology to see it. This is an astonishing coincidence, a reminder of how special this moment is. We are living at a time when we can discover and study visitors from other stars. Our ancestors could not do this, and our distant descendants might take it for granted. But for us, right now, it is new and exciting and full of wonder. This sense of wonder is what drives many scientists to study interstellar objects. It is not just about collecting data or publishing papers. It is about touching something that has travelled farther and longer than anything humans have ever built. It is about connecting with the universe in a deep and meaningful way. When you look at an image of 3I Atlas, you're not just seeing a fuzzy dot on a screen. You're seeing light that left the comet millions of kilometres away, travelled through space, entered Earth's atmosphere, passed through a telescope, and was captured by a camera. That light carries information about the comet, encoded in its colour and intensity. By decoding that information, we can learn about a world we will never visit, a star system we will never see, and a time in the galaxy's history that is forever in the past. Now let's bring the focus back to the present. As of November 2025, 3I Atlas is still visible, but it is fading fast. Astronomers are working hard to squeeze every bit of information they can out of the remaining observations. Every night that the comet is above the horizon, telescopes are pointed at it, taking spectra and images. Every measurement adds to the dataset, helping to refine our understanding. This is a race against time, a collective effort by scientists around the world to learn as much as possible before the window closes. What are some of the key questions they are trying to answer? One is the exact size of the nucleus. As mentioned earlier, estimates range from 440 metres to 5.6 kilometres, which is a big uncertainty. Pinning down the size more precisely would help scientists understand how much gas and dust the comet can produce, and how long it might stay active. Another question is the rotation rate. Like most asteroids and comets, 3I Atlas is probably spinning as it tumbles through space. Measuring how fast it spins and how its brightness changes with time can reveal the shape of the nucleus, and whether it has large-scale features like jets or active regions on one side. Scientists are also trying to understand the chemical composition in more detail. The initial observations showed high carbon dioxide and unusual metal ratios, but those measurements were taken when the comet was in certain parts of its orbit. As the comet moves farther from the Sun and cools down, different ices might start to dominate. By tracking how the composition changes over time, scientists can build a more complete picture of what the comet is made of. There is also the question of the anti-tail. If the sunward jet is real and not an optical illusion, what is causing it? One idea is that the solar wind, which is a stream of charged particles from the sun, is hitting the gas streaming off the comet and pushing it back toward the sun. This would require a very strong and dense outflow of gas, more than what typical comets produce. Another idea is that the comet's rotation is creating jets that point in unusual directions, and we are seeing one of those jets from an angle that makes it look like it is pointing sunward when it is actually pointing to the side. Resolving this question will require careful analysis of images taken from different angles and at different times. And then there is the big question: is 3I Atlas a natural object, or could it be something else? As mentioned earlier, Professor Loeb and some of his colleagues have raised the possibility that the comet's unusual features might be explained if it were artificial, like a probe from another civilization. This is a controversial idea, and most scientists do not think it is necessary to invoke such an exotic explanation. Natural comets are complicated, and we do not fully understand all the processes that can occur on their surfaces and in their atmospheres. But the fact that the question is even being asked shows how strange 3I Atlas is. It challenges our expectations and forces us to think carefully about what we're seeing. How would we ever know for sure if an interstellar object were artificial? The only way would be to study it up close, either with a flyby mission or, ideally, by landing on it and taking samples. If we found structure, like metal frameworks or electronic components, that would be a smoking gun. But short of that, it is hard to say. Even finding complex organic molecules would not prove anything, because organic molecules can form naturally in space. We would need to find something that clearly could not have formed without intelligent design. This is a high bar, and it might be impossible to meet based on remote observations alone. But it is worth thinking about, because if we ever did find evidence of extraterrestrial technology, it would be the most important discovery in human history. For now, the consensus among scientists is that 3I Atlas is a natural comet, albeit an unusual one. The features that make it strange can probably be explained by natural processes, even if we do not fully understand those processes yet. Comets are messy, complicated objects, and interstellar comets might be even messier because they formed under different conditions than our own comets. As we study more interstellar objects, we will get better at recognizing what is normal and what is truly anomalous. 3I Atlas is teaching us that normal might be more diverse than we thought. Let's take another moment to step back and recap. We have talked about how 3I Atlas was discovered, what it is made of, how it behaves, and what makes it unusual. We have compared it to the other two interstellar objects, Oumuamua and Borisov, and we have discussed what we can learn from studying these visitors. We have talked about the technology used to observe 3I Atlas, from ground-based surveys to space telescopes to spacecraft orbiting Mars. We have imagined future missions that might intercept interstellar objects and study them up close, and we have explored the philosophical implications of finding visitors from other star systems, including the possibility of panspermia and the question of whether any of these objects might be artificial. The common thread through all of this is curiosity, the drive to understand, to explore, and to connect with the universe beyond our own little corner of it. Now, as promised, let's talk about some related objects and topics that are being discussed in the space community. These are subjects that connect to 3I Atlas in various ways, whether through similar science, related missions, or shared themes of exploration and discovery. We will spend some time on each one, keeping the same friendly conversational tone, making sure everything is clear and easy to understand. Oumuamua holds a special place in the history of astronomy because it was the first interstellar object ever detected. Before October 2017, interstellar objects were purely theoretical. Astronomers knew they should exist based on our understanding of planetary formation, but no one had ever seen one. Then, on October 19, 2017, the Pan-STARRS telescope in Hawaii spotted a faint object moving through the solar system. At first, it was thought to be an asteroid or a comet, but as more observations came in, astronomers realized something was very different about this object. Oumuamua is a Hawaiian word that roughly translates to scout, or first distant messenger. The name was chosen by the Pan-STARRS team to honor the Hawaiian culture and language and to reflect the significance of this discovery. The object was moving on a hyperbolic trajectory, meaning it was not bound to the sun and would eventually leave the solar system. Tracing its path backward showed that it had come from the direction of the star Vega, though it did not originate from Vega itself. It had simply been travelling through that part of space when our solar system happened to be there. What made Oumuamua truly remarkable was its shape. Based on how its brightness changed as it tumbled through space, astronomers calculated that it was highly elongated, with a length roughly 10 times its width. Some estimates suggested it might be shaped like a cigar, while others proposed it might be more like a flat pancake. Either way, this was unusual. Most asteroids and comets are more or less round or only slightly elongated. An object with such an extreme shape raised questions about how it formed. Was it a fragment from a larger body that broke apart? Was it stretched out by tidal forces during a close encounter with a star or planet? Or was it something else entirely? Adding to the mystery, Oumuamua did not show any signs of cometary activity. There was no coma, no tail, no visible outgassing. This suggested that it might be made of rock and metal rather than ice, making it more asteroid-like. But then came the acceleration anomaly. As Oumuamua was leaving the solar system, astronomers noticed that it was moving slightly faster than it should have based on the sun's gravity alone. This extra acceleration was small, but it was real and measurable. The most likely explanation was that the object was outgassing, releasing a small amount of gas that acted like a tiny rocket. But if it was outgassing, why could we not see any evidence of it? Several ideas have been proposed to explain this mystery. One is that Oumuamua was covered in a dark organic crust that trapped gas underneath. As the sun heated the surface, gas built up pressure beneath the crust and eventually escaped through cracks or vents. Because the gas was released through small openings, it might not have created a visible coma. Another idea is that Oumuamua was made of nitrogen ice, similar to the surface of Pluto. Nitrogen ice sublimes at relatively low temperatures, so Oumuamua could have been outgassing even though it was far from the sun, and the gas might have been too faint to see. A third idea, proposed by Professor Loeb among others, is that Oumuamua might have been a thin, flat object pushed by the pressure of sunlight, like a solar sail. If it were artificial, built by an alien civilization, that would explain both its unusual shape and its acceleration without requiring outgassing. Most astronomers are skeptical of the artificial hypothesis. They point out that there are many natural processes that could explain Oumuamua's features, even if we do not fully understand them yet. The universe is full of surprises, and just because something is unusual does not mean it is artificial. However, the debate has been healthy for the field. It has encouraged astronomers to think carefully about what would constitute evidence of extraterrestrial technology, and it has highlighted the need for better observations of interstellar objects. Oumuamua is now long gone, far beyond the reach of even our most powerful telescopes. By 2025, it is somewhere out past the orbit of Saturn, continuing its journey through the galaxy. We will never get another chance to study it. This is one of the frustrations of interstellar object astronomy. These visitors do not stick around. By the time we realize what we're seeing and mobilize our resources to study it, the object is already leaving. Oumuamua was visible for only a few weeks before it faded from view. During that time, astronomers took every measurement they could, but there were limits to what could be done on such short notice. The legacy of Oumuamua is that it opened our eyes to the possibility of interstellar visitors. It showed that these objects are out there, and that we can detect them if we look carefully. It also showed that each one is unique and might challenge our expectations. Oumuamua was not a typical comet or a typical asteroid. It was something new, something we had never seen before. And that is what makes these discoveries so exciting. Every interstellar object is a mystery waiting to be solved. If Oumuamua was the strange, mysterious first visitor, 2I Borisov was the friendly, familiar second one. Discovered on August 30th, 2019, by amateur astronomer Gennady Borisov, this comet looked like what astronomers expected an interstellar comet to look like. It had a bright, active coma and a long, sweeping tail. It followed a hyperbolic trajectory, proving that it came from outside the solar system, but in most other ways, it resembled the comets we know and love. Gennady Borisov discovered the comet using a homemade telescope with a 65-centimeter mirror, which he had built himself over several years. He was scanning the sky from the Margot Observatory in Crimea when he noticed a faint, fuzzy object that did not match any known comet or asteroid. He reported his observation to the Minor Planet Center, and within days, other astronomers confirmed that this was indeed an interstellar object. The discovery was announced on September 11, 2019, and the comet was officially designated 2I Borisov, marking it as the second interstellar object ever detected. Borisov reached perihelion on December 8, 2019, at a distance of about 307 million kilometers from the Sun, which is about twice the distance from Earth to the Sun. This was farther out than Oumuamua had come, so the comet never got as warm or as bright, but it was still active enough to produce a beautiful coma and tail that could be seen through telescopes around the world. Astronomers seized the opportunity, and Borisov became one of the most intensely studied comets in history. Telescopes on every continent observed it, taking images and spectra to learn as much as possible about its composition and behaviour. One of the key findings was that Borisov had a lot of carbon monoxide, much more than typical comets from our solar system. Carbon monoxide is a gas that freezes at very low temperatures, even lower than the temperature at which water freezes. This suggests that Borisov formed in a very cold part of its home system, far from its parent star, where temperatures were so low that even carbon monoxide could condense into ice. This tells us something important. The planetary system that Borisov came from probably had its comet-forming region much farther out than our own solar system's comet-forming region. Scientists also studied the dust coming off Borisov. They found that the dust particles were similar in size and composition to the dust in solar system comets, but there were some differences. The ratio of dust to gas was slightly different, and the way the dust scattered light suggested that the particles had a slightly different structure. These subtle differences hint that even though Borisov looked familiar, it was not exactly the same as our comets. It formed in a different environment, under different conditions, and those differences left traces in its composition and behaviour. One of the most exciting observations of Borisov came from the Hubble Space Telescope, which took sharp images showing the comet's nucleus and coma in great detail. These images revealed that the nucleus was probably less than a kilometre across, smaller than many comets in our solar system. Despite its small size, Borisov was quite active, producing a coma that was thousands of kilometres wide. This high level of activity suggested that the nucleus was rich in volatile ices, substances that evaporate easily when warmed. Another interesting discovery was that Borisov appeared to be fragmenting, or breaking apart as it approached the Sun. Images taken in March 2020, several months after perihelion, showed that the comet had developed a secondary nucleus, a smaller chunk that had separated from the main body. Comets do this sometimes when the stresses from heating and outgassing become too much, causing pieces to break off. The fragmentation of Borisov gave scientists a rare opportunity to study the interior structure of an interstellar comet. By watching how the fragments behaved, they could learn about the strength and composition of the material deep inside the nucleus, material that had been hidden beneath the surface until the breakup exposed it. Borisov eventually faded from view in early 2020, about 6 months after its discovery. By that time, it had provided astronomers with a wealth of data, more than had been collected for any previous interstellar object. The lessons learned from Borisov helped scientists prepare for future discoveries. They now knew what an interstellar comet could look like, how bright it might be, and what kinds of observations would be most useful. This knowledge is being applied to the study of 3I Atlas, and it will be applied to future interstellar visitors as well. The discovery of Borisov also highlighted the important role that amateur astronomers can play. Gennady Borisov did not have access to a professional observatory or a large research budget. He was passionate about astronomy and dedicated his time and resources to building a telescope and scanning the sky. His discovery shows that you do not need to be a professional to make a significant contribution. All you need is curiosity, persistence, and the willingness to look where others might not be looking. While 3I Atlas is already on its way out of the solar system, scientists are looking ahead to future interstellar visitors. The European Space Agency's Comet Interceptor mission represents a new approach to studying these objects. Instead of launching a spacecraft to a specific target that is already known, Comet Interceptor will be sent into space without a predetermined destination. It will wait in orbit, ready to intercept a suitable comet or interstellar object when one is discovered. This mission is scheduled to launch in 2029, piggybacking on another spacecraft to save costs. Once in space, Comet Interceptor will travel to a special location called the Sun-Earth Lagrange Point 2, or L2 for short. This is a spot in space about 1.5 million kilometers from Earth, on the opposite side from the Sun. At L2, the gravitational pull of the Sun and Earth balance out in just the right way that a spacecraft can stay there with very little fuel, essentially hovering in place. Several other spacecraft, including the James Webb Space Telescope, are stationed at L2 because it provides a stable, quiet environment with an excellent view of deep space. Comet Interceptor will park at L2 and wait, possibly for several years, until astronomers on Earth discover a suitable target. The ideal target would be a long-period comet, one that is visiting the inner solar system for the first time and has never been warmed by the sun before. Such a comet would be pristine, still containing the original material from when it formed billions of years ago. If an interstellar object were to be discovered heading inward, and if the timing and trajectory were right, Comet Interceptor could potentially intercept that instead. This would be an incredible opportunity the first time humanity has sent a spacecraft to study a visitor from another star system up close. The mission design is clever and innovative. Comet Interceptor actually consists of 3 separate spacecraft traveling together. There is a main spacecraft built by ESA and 2 smaller companion probes, one built by the Japanese space agency JAXA and another built by ESA. When the spacecraft approach the target comet, they will separate and fly past it from different angles, all at the same time. This multi-point observation strategy will give scientists a 3-dimensional view of the comet, showing its shape, structure, and activity from multiple perspectives simultaneously. Each spacecraft will carry a suite of instruments designed to study different aspects of the comet. There will be cameras to take close-up pictures of the nucleus, showing craters, cliffs, jets, and other surface features. There will be spectrometers to analyze the composition of the gas and dust streaming off the comet, identifying the molecules and elements present. There will be dust analyzers to collect and examine individual dust particles, measuring their size, shape, and composition. And there will be magnetometers and plasma instruments to study how the comet interacts with the solar wind and the sun's magnetic field. One of the exciting aspects of Comet Interceptor is that it will be able to respond to targets of opportunity. If a particularly interesting comet or interstellar object is discovered, the mission can be redirected to intercept it, even if it was not part of the original plan. This flexibility is crucial because we cannot predict when the next interstellar visitor will arrive or what path it will take. By having a spacecraft already in space and ready to go, we maximize the chances of being able to study one of these rare objects. The mission also represents a new way of thinking about space exploration. Traditionally, missions are planned years or even decades in advance, with every detail worked out before launch. But with fast-moving targets like interstellar objects, there is not enough time for that kind of planning. Comet Interceptor is designed to be responsive and adaptable, able to make quick decisions and change course on short notice. This is sometimes called agile space exploration, and it might become more common in the future as we deal with unpredictable phenomena and fleeting opportunities. If Comet Interceptor successfully intercepts an interstellar object, the data it returns will be transformative. For the first time, we will have close-up images of a visitor from another star system. We will be able to see the texture of its surface, the shapes of its features, and the details of how it releases gas and dust. We will be able to measure its composition directly, without having to rely on remote observations that can be ambiguous or uncertain, and we will be able to compare it in detail to comets from our own solar system, identifying the similarities and differences that tell us about the diversity of planetary systems in the galaxy. Even if Comet Interceptor does not encounter an interstellar object, it will still achieve important science by studying a pristine long-period comet. These comets come from the Oort cloud, a vast reservoir of icy bodies that surrounds the solar system at a great distance. Objects in the Oort cloud have been frozen for billions of years, preserving the original material from the solar system's formation. Studying them is like opening a time capsule, giving us a direct look at what the early solar system was like. So no matter what target Comet Interceptor ends up visiting, it will provide valuable insights into the history and evolution of planetary systems. To understand where comets come from, we need to talk about the Oort cloud. This is a theoretical region of space that surrounds our solar system like a giant spherical shell. It is named after the Dutch astronomer Jan Oort, who proposed its existence in 1950 based on the orbits of long-period comets. No one has ever directly observed the Oort cloud because it is so far away, and the objects in it are so faint. But the evidence for its existence is strong, based on the behavior of comets that occasionally visit the inner solar system. The Oort cloud is thought to extend from about 2,000 astronomical units from the Sun all the way out to 100,000 astronomical units or more. 1 astronomical unit, or AU, is the distance from the Earth to the Sun, about 150 million kilometers. So the inner edge of the Oort cloud is about 2,000 times farther from the Sun than Earth is, and the outer edge might be 100,000 times farther. At those distances, the Sun is just a bright point of light, no bigger or brighter than any other star in the sky. The Oort cloud is so far out that it is almost halfway to the nearest other star. How did the Oort cloud form? The current theory is that it consists of icy planetesimals that formed in the region where the giant planets are now, closer to the Sun. When Jupiter, Saturn, Uranus, and Neptune were growing, their gravity scattered many of these icy bodies. Some were thrown inward toward the Sun, some were thrown outward, and some were thrown completely out of the solar system, becoming interstellar objects like 3I Atlas. The ones that were thrown far out, but not quite fast enough to escape, settled into distant orbits, forming the Oort cloud. The Oort cloud is estimated to contain trillions of icy bodies, ranging in size from small chunks a few meters across to massive objects hundreds of kilometers wide. Most of them will never come close to the Sun. They will remain frozen in the outer darkness forever, but occasionally something disturbs one of them. Maybe a nearby star passes through the outer part of the solar system, and its gravity tugs on the Oort cloud objects. Maybe the gravitational pull of the entire Milky Way galaxy causes a ripple, or maybe random interactions between objects in the Oort cloud itself cause one of them to change its orbit. Whatever the cause, sometimes an object is nudged onto a path that brings it inward, toward the Sun. These are the long-period comets that take thousands or even millions of years to complete one orbit. When they enter the inner solar system for the first time, they are pristine, never having been warmed by the Sun. As they approach, the Sun's heat starts to sublimate the ice on their surface, and they develop a coma and tail. Many long-period comets have orbits that are nearly parabolic, meaning they come very close to the Sun once, and then head back out to the Oort cloud, not to return for thousands of years. A few of them get gravitationally perturbed by the planets during their visit, and their orbits are changed, either sending them out of the solar system entirely or capturing them into shorter period orbits. The Oort cloud is not the only reservoir of comets. There is also the Kuiper belt, which is much closer to the Sun, extending from about 30 AU to 50 AU, just beyond the orbit of Neptune. The Kuiper belt is shaped like a flattened disk rather than a sphere, and it contains icy bodies similar to those in the Oort cloud. Short-period comets, which orbit the Sun every few years or decades, come from the Kuiper belt. Pluto is the most famous object in the Kuiper belt, but there are thousands of others, and new ones are being discovered regularly. Both the Oort cloud and the Kuiper belt are important for understanding the history of the solar system. They are the leftovers, the material that did not get incorporated into planets. By studying the comets that come from these regions, scientists can learn about the conditions in the early solar system and how planets formed. And by comparing our cometary reservoirs to those that probably exist around other stars, we can learn whether our solar system is typical or unusual. Interstellar objects like 3I Atlas are essentially comets from other stars' Oort clouds or Kuiper belts. They were ejected from their home systems and have been travelling through the galaxy ever since. When one of them passes through our solar system, it is like receiving a sample from another star's planetary debris. This is why interstellar objects are so valuable. They let us compare our solar system to others without having to travel light years to get there. The discovery of 3I Atlas was made by the Atlas Survey, which is primarily designed to find near-Earth objects, or NEOs. These are asteroids and comets whose orbits bring them close to Earth. Some of them pose a potential threat. If a large asteroid were to collide with Earth, it could cause massive destruction, potentially even threatening human civilization. The goal of planetary defense is to identify these threats early and develop ways to deflect or destroy them before they can hit us. Atlas is one of several survey programs around the world that scan the sky every night, looking for moving objects. When an object is detected, its position is measured and reported to the Minor Planet Center, which calculates its orbit. If the orbit brings the object close to Earth, it is flagged for further observation and monitoring. Over the years, thousands of near-Earth asteroids have been discovered, and scientists are constantly refining the catalogue, looking for any that might pose a danger in the coming decades or centuries. Most near-Earth objects are small and harmless. If they were to hit Earth, they would burn up in the atmosphere or explode high above the ground, causing little or no damage. But larger objects, those bigger than about 140 meters across, could cause significant destruction if they hit a populated area. And really large objects, those a kilometer or more across, could cause global catastrophes, triggering tsunamis, earthquakes, and climate changes that could threaten life on Earth. Fortunately, such objects are rare, and most of the large ones have already been discovered and tracked. None of them are on a collision course with Earth in the foreseeable future. Still, the possibility of an impact is real, and scientists take it seriously. In recent years, there have been major advances in planetary defense. In 2022, NASA launched a mission called DART, which stands for Double Asteroid Redirection Test. This spacecraft deliberately crashed into a small asteroid moon called Dimorphos, changing its orbit around its parent asteroid. The mission was a test of kinetic impact, one of the methods that could be used to deflect a dangerous asteroid. The impact was successful, demonstrating that we have the technology to change an asteroid's path if we need to. The Atlas survey played a role in observing the results of the DART impact. Telescopes around the world, including Atlas, watched as the impact created a plume of dust and debris, and they measured how much Dimorphos's orbit changed. This kind of international collaboration is essential for planetary defense. No single country or organization can monitor the entire sky by itself. It takes a global network of telescopes and scientists working together to identify threats and develop responses. Interestingly, the techniques used for planetary defense are also useful for studying interstellar objects. When 3I Atlas was observed from Mars by spacecraft that are part of ESA's planetary monitoring network, it was an exercise in using multiple viewpoints to track a moving object. This same technique could be used to precisely track a threatening asteroid, allowing scientists to predict its path and plan a deflection mission. In a way, every interstellar object we discover is a practice run for planetary defense, helping us refine our methods and improve our capabilities. It is worth noting that interstellar objects themselves are not a threat. They are passing through too quickly to be captured by Earth's gravity, and their orbits are well understood once they have been observed for a few days. The chances of an interstellar object actually hitting Earth are incredibly small, far smaller than the chances of being hit by an asteroid or comet from our own solar system. So while we study interstellar objects with great interest, we do not need to worry about them posing a danger. Interstellar objects like 3I Atlas are connected to the broader field of exoplanet research. Exoplanets are planets that orbit stars other than the Sun. The first confirmed exoplanet around a Sun-like star was discovered in 1995, and since then, thousands more have been found. The study of exoplanets has transformed our understanding of planetary systems and has shown that planets are common throughout the galaxy. Most exoplanets are detected using indirect methods. One common technique is the transit method, where astronomers watch a star and look for a tiny dip in its brightness when a planet passes in front of it. Another technique is the radial velocity method, where astronomers measure the wobble in a star's motion caused by the gravitational pull of an orbiting planet. Both methods have been incredibly successful, but they have limitations. They work best for planets that are close to their stars, and they provide limited information about the planet's composition and atmosphere. Interstellar objects offer a complementary way to learn about other planetary systems. Instead of detecting the planets themselves, we are detecting the debris, the comets and asteroids that were left over from planet formation or were ejected during the system's evolution. By studying the composition of these objects, we can infer what the planets in those systems might be like. For example, if an interstellar comet has a lot of water ice, it suggests that the planetary system it came from had conditions favourable for forming icy bodies, which might also mean it has planets with oceans. If an interstellar object has unusual minerals or organic compounds, it might tell us about unique chemical processes happening in that system. The number of interstellar objects we have detected so far is small, just 3 confirmed ones. But as our detection capabilities improve, we will find more, and we will be able to start doing statistical studies. We will be able to ask questions like, what fraction of planetary systems eject comets versus asteroids? Are interstellar objects more common from systems with certain types of stars? Do older systems produce different kinds of interstellar objects than younger systems? These questions connect directly to the study of exoplanets, because the answers will tell us about the diversity of planetary systems and the processes that shape them. There is also the exciting possibility of detecting exocomets, comets that are still orbiting their parent stars. This has been done a few times using the transit method. When a comet passes in front of a distant star, it can cause a temporary dip in the star's brightness, similar to what a planet does but with a different light curve pattern because of the comet's tail. Observing exocomets gives us a snapshot of a planetary system's cometary population at the current time, while interstellar objects give us samples that have been travelling for millions or billions of years. Together, these two types of observations help us build a complete picture. Another connection is the search for habitable planets. One of the big questions in exoplanet research is whether any of these planets could support life. For a planet to be habitable, it needs to be in the right location, not too hot and not too cold, so that liquid water can exist on its surface. It also needs to have the right kind of atmosphere and enough water. Interstellar objects can tell us something about water distribution in other planetary systems. If we find that interstellar comets are generally water-rich, it suggests that water is common in the galaxy, which increases the chances that habitable planets are common too. The study of interstellar objects and the study of exoplanets are two sides of the same coin. Both are trying to understand planetary systems beyond our own. Both are pushing the boundaries of our technology and our knowledge, and both are driven by the same fundamental question: are we alone in the universe? While finding life on another planet would require much more direct evidence, every piece of information we gather about other planetary systems brings us one step closer to answering that profound question. The discovery and study of 3I Atlas would not have been possible without the telescopes and instruments that exist today. But the field is about to take a huge leap forward with the next generation of telescopes coming online in the next few years. These new instruments will be far more powerful than anything we have now, and they will transform our ability to detect and study interstellar objects. One of the most anticipated is the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, or LSST. This telescope is being built in Chile, and it is expected to begin operations in the mid-2020s. The Rubin Observatory has a unique design. It has a very wide field of view, able to image large swaths of the sky at once, and it is equipped with a giant camera that has 3.2 billion pixels, making it one of the largest digital cameras ever built. The plan is for the Rubin Observatory to scan the entire visible sky every few nights, creating a continuous movie of the universe. This will allow it to detect anything that moves or changes, from asteroids and comets in our solar system to supernovae in distant galaxies. For interstellar objects, the Rubin Observatory is a game changer. It is estimated that the telescope will detect one interstellar object per year, maybe more. This will build up a catalogue of these visitors, allowing scientists to study them as a population rather than as individual oddities. With dozens or even hundreds of interstellar objects detected over the course of the observatory's lifetime, we will be able to answer fundamental questions about their origins, compositions, and trajectories. We will learn how many interstellar objects are passing through the solar system at any given time, what size range they span, and whether certain types are more common than others. The Rubin Observatory will also be able to detect interstellar objects earlier, when they are still farther from the Sun. This will give scientists more time to plan follow-up observations with other telescopes and possibly even plan spacecraft missions if the object is particularly interesting and accessible. The early detection is crucial because interstellar objects move quickly, and the window for studying them is short. The sooner we spot them, the more we can learn. Another major facility is the Extremely Large Telescope, or ELT, being built by the European Southern Observatory in Chile. This telescope will have a mirror 39 meters across, making it the largest optical telescope in the world when it is completed. The sheer size of the mirror means the ELT will be able to collect far more light than any existing telescope, allowing it to see fainter objects and take more detailed spectra. For interstellar objects, this means we will be able to study their composition with unprecedented precision, identifying molecules and elements that are too faint to detect with current instruments. The ELT will also be able to take extremely high-resolution images, potentially resolving details on the surface of large asteroids or the nuclei of comets. While it's unlikely that the ELT could directly image the nucleus of a small interstellar object like 3I Atlas, it could certainly provide detailed views of the coma and tail, showing structures like jets and streamers that reveal how the comet is releasing material. There are also space-based telescopes in development. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will have a wide field of view like the Rubin Observatory, but with the clarity and sensitivity of a space telescope. It will be particularly good at detecting faint moving objects and could contribute to the search for interstellar visitors. The James Webb Space Telescope, already in operation, will continue to play a crucial role, providing detailed infrared spectra of interstellar objects to reveal their chemical composition. All of these telescopes will work together, forming a global and space-based network that can respond quickly to new discoveries. When an interstellar object is detected by a survey like ATLAS or the Rubin Observatory, other telescopes can immediately follow up, taking the detailed observations needed to understand what the object is and where it came from. This kind of rapid, coordinated response is essential for maximizing the scientific return from these fleeting visitors. The next decade or two promises to be an incredibly exciting time for interstellar object research. We are on the verge of transitioning from a situation where finding one of these objects is a rare, lucky event to a situation where we routinely detect and study them. This will open up entirely new areas of research and will answer questions that we can barely ask today. What is the typical composition of interstellar objects?